Hello everyone. In today's lesson we're going to be talking about properties of light. And in science we refer to light as electromagnetic radiation. Light is a form of electromagnetic radiation, which is a form of energy that exhibits wave-like behavior as it travels through space. So in our lesson today we're going to be looking at wave properties of light, but we're also going to look at some characteristics of light that are not consistent with wave behavior. So we end up seeing some curious outcomes when we study the properties of electromagnetic radiation. First of all, just a heads up, electromagnetic radiation is sometimes abbreviated as EMR. So if you see this EMR acronym, that's what we're referring to, electromagnetic radiation. As the definition states here, electromagnetic radiation or light does have wave characteristics. It behaves as a wave in many situations. So when we think about waves, water waves, sound waves, waves arise from vibrating objects. In the case of a water wave, it could be something bobbing up and down in the water to create ripples. In the case of a sound wave, perhaps you've plucked a string on a guitar and the vibration of that string creates sound waves. With electromagnetic radiation or light, the vibrating object is an electric charge, specifically electrons. So vibrating electrons produce electromagnetic radiation. And if we look at the vibration of the electron, the oscillation, that's another word for an object that moves back and forth about an equilibrium position, oscillation. If we look at the oscillation of an electron and measure its displacement as a function of time, so x for displacement versus t for time, what we end up with is a sine curve. So we would get something that looks like this. So modeled graphically, wave behavior, specifically here we're looking at a vibrating object as it oscillates about an equilibrium position. The equilibrium position would be the horizontal axis in this graphical representation. We end up with a sine curve when we plot that oscillation as a function of time. And then from this sine curve, we can get some really important information about the wave itself. The first measurement that we might make for this sine curve would be a measurement of the wavelength. And that would be the distance between successive identical wave parts. So for instance, if we measure the distance between these two wave peaks, successive wave peaks, this distance is referred to as one wavelength. And the symbol for wavelength that we use in science is a Greek letter lambda. Kind of looks like an upside down Y a little bit. And again, this would be measured in units of length, so meters. With electromagnetic radiation, sometimes wavelengths are very, very small. So we will use nanometers frequently. So 1 nanometer is equivalent to 10 to the negative 9th meters. It's something that we'll see in the calculations that we'll be doing in class. So we're looking at very, very small wavelengths for some types of electromagnetic radiation and much, much larger wavelengths for other types of electromagnetic radiation. There's a lot of variation. We'll talk about that more in just a second. So wavelength is the distance between successive identical wave parts. And it could be any successive identical wave parts. We don't necessarily have to go from peak to peak. We could go from equilibrium to equilibrium as we go negative amplitude to positive amplitude and measure this distance as one wavelength as well. This would be the exact same measured wavelength as what we saw when we looked at the distance between the successive peaks, assuming the wavelength of the wave is constant. So wavelength measured in meters or nanometers or any other unit of measurement of length is going to be a characteristic of waves, including light, electromagnetic radiation, that we will quantify. We can also look at the amplitude of this wave. And going back to our discussion earlier about the fact that what we're actually measuring here is how far an electron moves away from its starting position or equilibrium position as it oscillates back and forth. So we're going to have an electron oscillating back and forth, back and forth. We're plotting that oscillation as a function of time here. If we look at the maximum displacement from equilibrium, so the distance from the equilibrium position to the peak or the valley. We call these crests and troughs on a graph of a wave oscillation. This is what's referred to as amplitude. And like wavelength, it's a measure of distance, so meters or any equivalent measurement of length or distance would be acceptable here. So amplitude is the position of maximum displacement, or the magnitude of maximum displacement from equilibrium on a wave. Finally, what we would be interested in from an electromagnetic radiation standpoint is a concept related to wavelength, and we'll see that in just a second here, but it's called frequency. So frequency explains or describes how often a wave repeats itself. Now this is going to be hard to illustrate on the graph, but what we would be looking at is how many times we see identical wave parts per unit time. So maybe we look at the peaks, at the wave crests, and I would be counting how many wave crests do I see in every second. And then that would describe the frequency of the wave, how often the wave repeats itself. Now, in chemistry, we use a Greek letter nu, which sort of looks like a lowercase v, but it's different. It's a lowercase Greek letter nu. We use that to represent frequency in chemistry class. Now, since frequency is measuring how many times something occurs in a given time frame, it actually has units of reciprocal time, or 1 over time. So a lot of times this will be seconds to the negative first power, or 1 over seconds. We have a special name for that unit of reciprocal seconds. In science, we call it hertz, capital H, lowercase z. So you could use either the seconds to the negative first or the hertz designation as a label for frequency if you're counting the number of times something occurs per second. So wavelength, amplitude, frequency, 3 common characteristics of waves that will apply to our discussion of electromagnetic radiation going forward. Another thing that we might look at here would be wave speed. So wave speed, if we think about speed from math class or physics class or wherever you've looked at calculations of speed before, it's distance divided by time. So how far something travels in a unit time. So let's get ourselves a little bit of space here so we can talk a little bit about wave speed before we go forward. So distance divided by time, that's units of distance per time. So we would be looking at units like meters per second or miles per hour, kilometers per hour when we're talking about speed. We find for waves that wave speed, we're going to use, that's not what I want. Okay, so wave speed, we find wave speed, and we're going to use a lowercase letter v for wave speed, is related to wavelength and frequency. In fact, it's equal to the product of wavelength and frequency. Now this gets a little bit confusing because we have two variables that look a lot like each other here. We've got a lowercase v, and that is our variable for speed. And then we've got the lowercase Greek letter nu, which looks a lot like a lowercase v, but it's not. That represents frequency. So how does this equation make sense in terms of what we know about speed from math class, let's say? Well, remember that we said speed equals distance divided by time. So that could be something like meters per second. We'll take a look at what we have in the equation v equals lambda nu. We've got wavelength, which could be measured in meters or any other unit of length. And then we've got frequency, which we said earlier had units of reciprocal time, so seconds to the negative first, or 1 over seconds. Well, that's meters per second. We're getting the exact same dimensions with wavelength times frequency as we get when we take distance divided by time. So this equation, v equals lambda nu, is in fact consistent with the traditional definition of speed, as it has units of distance or length per time. So, interesting, for light, for electromagnetic radiation, what we find is that wave speed is always the same thing. It's always constant. And it's a very, very fast speed for light waves, for electromagnetic radiation. It's equal to 3.00 times 10 to the 8th power meters per second. So a very, very large magnitude we see for all electromagnetic waves. We call this value the speed of light. All light waves travel at this speed in a vacuum, specifically if there is no other factors influencing the speed of light in a vacuum where there's no air or other matter to interact with. 3.00 times 10 to the 8th meters per second is the speed of light. So we treat this as a physical constant, and instead of calling it v, we actually use the variable lowercase c. So we say c is equal to 3.00 times 10 to the 8th meters per second. So we're going to change our speed equation a little bit here. For light, we can say that c equals lambda nu. And since that speed value is constant, 3.00 times 10 to the 8th meters per second, what we see is that wavelength and frequency are inversely proportional. So lambda and nu are inversely related. So what does that mean? Well, inverse relationship means that when one of the variables increases, the other has to decrease proportionately. So if we were to double the frequency of our wavelength, 2 times the value of nu, we would have to have 1/2 the wavelength in order to maintain the same speed. So doubling the frequency halves the wavelength. That's an inverse proportionality or an inverse relationship between wavelength and frequency. So what we end up finding on a graph of a wave, if we look at the sine curve like we did earlier, for a wave that has high frequency, it has a very short wavelength. So the distance between the successive wave crests would be short. But for a wave that has a low frequency, it would have a much longer wavelength because lambda and nu are inversely proportional. So that's a little quick overview of the properties of waves. That equation c equals lambda nu is going to be important later on, so be sure you've got that written down somewhere, as well as this value for the speed of light in a vacuum, 3.00 times 10 to the 8th meters per second. Now, I said earlier when we were talking about wavelength that nanometers is frequently a unit of measurement that we use to measure the wavelength of electromagnetic radiation. But some electromagnetic radiation has much, much longer wavelengths that can be measured in other units, maybe even meters. So we need to investigate just a little bit here the differences in frequency and wavelength for electromagnetic radiation and what we call the electromagnetic spectrum. So let's take a look at this little graphic here. This is an outline of what's referred to as the electromagnetic spectrum. And this is arranged in order of increasing frequency in this example. So we've got the lowest frequency on the left side and the highest frequency on the right side. We're going from 10 to the 4th hertz on the left all the way to 10 to the 20th hertz on the right. So frequency is increasing from left to right. The different portions of electromagnetic radiation with different frequencies are given special names in science. So the very, very low frequency waves are what we refer to as radio waves. A little bit higher frequency than radio waves are microwaves. A little bit higher frequency than that still we call infrared. Oops. Just higher in frequency than infrared radiation, we have visible light. So you see your Roy G. Bibb right here. This is our visible spectrum. These are the frequencies of electromagnetic radiation that we can see. As we move higher in frequency, we see ultraviolet comes next. After ultraviolet, we have X-rays. And then finally, the highest frequency electromagnetic radiation referred to as gamma rays or gamma radiation. So we have different names for electromagnetic radiation depending on its frequency. Or alternatively, you could think about this in terms of wavelength. Remember that we said that frequency and wavelength are inversely related? So if I have the lowest frequency on the left side of my line and the highest frequency on the right, we would have the inverse if we look at wavelength. We would have the shortest wavelength on the right side and the longest wavelength then on the left. So increasing wavelength goes in the opposite direction on this image, on this graphic of the electromagnetic spectrum. So we've got different types of electromagnetic radiation depending on frequency or wavelength. And this electromagnetic spectrum illustrates where those types of electromagnetic radiation fall in relation to each other in terms of their frequency. It should be noted that the visible spectrum is a pretty small segment of this overall electromagnetic spectrum. So the frequencies that we can see are quite small. Of course, you'll recognize some of these other types of electromagnetic radiation like X-rays and ultraviolet radiation. There are lots of uses for the other types of electromagnetic radiation as well. So it's not as though we're only interested in visible light. That just happens to be the only frequencies of EMR that we can see. So that's a pretty good overview then, I think, of wave characteristics of light. This is where things get a little bit interesting. So what we find with electromagnetic radiation is that while we can explain many of light's behaviors, many of light's characteristics with wave theory, we can't explain all of light's behaviors with wave theory. There are some characteristics of light that are inconsistent with the wave model